Welcome to my talk here at DAC. I am Jeff Wittick. I'm the Chief Product Officer at Ampere Computing, and I want to talk a little bit about what's changing in the AI space. What are the implications from a technology perspective, and what are some of the things that we need to do from a silicon perspective to keep pace and to stay ahead of some of these trends. But since we're here in San Francisco, I thought I'd start a little bit further back. So back in 1848, about 100 miles northwest of here, gold was discovered at Sutter's Mill. And that sparked a huge gold rush and a big boom period. And as a result of the gold rush, we had a lot of winners and a lot of losers. The remnants of some of those winners are still around. We're a couple blocks north of Brannan Street. So Samuel Brannan made a fortune selling supplies to miners, building stores that serviced miners' needs, and also in real estate. Levi Strauss, so Levi's Jeans, headquartered still here in San Francisco. Actually, a descendant of that fortune is the mayor of San Francisco right now. They also have a lasting legacy from the gold rush, from selling pants, blue jeans, to the miners. And then San Francisco, where we are here, and then Sacramento, they experienced huge growth. There were only 1,000 people that lived in San Francisco at the time of the gold rush. The population increased by 25x that year. In 1850, California became a state, and Sacramento became the state capital a couple years later, all because of the massive growth that occurred because of the gold rush. Now, there weren't only winners, there were a lot of losers in the gold rush as well. Many of the miners ended up penniless. They didn't make any money at all at the end. Also, the local population. Most of the local populations, the indigenous people, they were negatively impacted by the growth from the gold rush. And then the environment. There was a massive negative impact to the environment, whether it was the mercury that was being used to separate out gold, whether it was some of the hydraulic drilling that was used that ended up wrecking a lot of the landscape. There was a lot of deforestation. So why does this matter? We've seen these boom periods over and over again. And so while there are big winners, there's often also losers, and the impacts of these periods can be felt for a really long time, 175 years later. So there's a lot of lessons that we can learn as we look back at some of these previous growth periods. Now let's go to one that's in our lifetimes, the big internet build out. This is one that probably a lot of us here are very familiar with. The first network that was available to every researcher was NSFNet, and that was really the main US internet backbone back in the 90s. It grew from 2,000 computers in 1986 to 2 million computers by 1993. The success of NSFNet, though, sort of doomed it in the sense that the National Science Foundation shut down NSFNet in 1995, and then they left it to private companies to run the internet from then on. So after that point, Sprint, MCI, AT&T, they started to run the fiber that was located across the United States. And shortly after that time, in 1996, the Telecommunications Act of '96, that further deregulated the market even further. So it opened up the market to many new entrants. At this point, any communications business could now compete in any market against each other. And at this point, the long-distance telecom monopoly was over. That fueled many new entrants into this market. Local telephone companies, long-distance companies, cable companies, new emerging ISPs, all of these folks could compete against each other, and they could build last mile partnering with NSPs as well. And that created a big frenzy. Some names that you see here, people like Global Crossing, Enron, Quest, Lucent, Level 3. They all raced to build out fiber across the network. A lot of companies started offering ISP services. They built local networks, and they participated in the growth. And then there were a lot of telecom equipment providers as well. Cisco, Ciena, Lucent, Nortel, others, they all sought to profit in this giant build out. So this race began to build out networks at bigger and bigger scale. IT spend increased incredibly rapidly, well into double-digit percentage increases year over year. And why were people racing and building out so much fiber? Well, it was actually partly based on incorrect information. WorldCom had gone out and said that every 100 days, internet traffic was doubling. And so that spurred people to keep up. Now, in reality, internet traffic was only doubling about once a year. And so there was a lot of hype here. People were building out network faster than it could really even be consumed. But despite all that hype, and kind of the unnecessary build out that occurred in some places, this growth was creating a lot of productivity gains. As companies began to add internet capabilities into their business models, US economy saw one of its greatest surges in productivity that we've ever seen. Hourly productivity increased by 13%. That's a really, really massive increase in productivity. So all of that IT spending, while it may have been overblown, it did have very, very positive impacts on the economy. And this created this virtuous cycle where as the technology improved everybody's lives, productivity gains in turn spurred more and more growth. And so the idea was that the more money that we spent on IT, the more we could increase productivity. Now, unfortunately, this all did come to a pretty sudden end. At the peak, the annual CapEx in telecom was $120 billion, which in today's dollars is $225 billion. So it's one of the biggest capital expenditures we've ever seen in building out technology. And this did end up creating a massive glut in fiber, and it took about a decade for all that fiber to be consumed. In 2000, for a variety of different financial reasons, the bubble popped, and telecom and hardware were hit pretty hard, and telecom spending then crashed. So what can we learn from that period that could be relevant to us today as we build out AI? One, the projections on how fast things were building out, how fast demand was growing, they were overinflated. The spending numbers just didn't match, the revenue numbers didn't match the spending, at least at the time. It took about a decade for that to catch up. In 1999, the annual per capita spend on telecom was $800 per person in the US. So massive amount of spend, and clearly there wasn't $800 of revenue being generated at that time. So the marginal increases in fiber spend weren't generating the same marginal increases in revenue. So that people learned all those big marginal, the massive exponential build out in fiber couldn't keep up, at least in that time frame. In 2000, e-commerce was about $27 billion. And as we know, e-commerce has been one of the biggest reasons why this internet build out has proven to be incredibly successful and productive. So $250 billion was spent in 2000 on fiber. E-commerce was generating about $27 billion. Finally, in about 2012, the total e-commerce business in the US exceeded $225 billion for the first time. So it took about 12 years, but eventually all that spending was in fact justified. And today, e-commerce in the US is a $1.2 trillion market. Even though there were people like Pets.com and Webvan that disappeared and failed, there were other success stories like Amazon, which today is the second largest retailer of any type in the world. So across history, every one of these big tech cycles has been accompanied by big capital bubbles. This actually happened back in the 1700s as canals were built across the UK. There was a massive spending bubble. A lot of people lost money, but it created lasting infrastructure that ended up being incredibly valuable for many, many centuries. Same thing in railroads in the 1800s, big spending bubble, but in the end, the railroad network has proven to be extraordinarily valuable even today. The other thing that happens oftentimes in these cycles is that the technology developments end up outpacing people's expectations. So with the fiber build out, it was expected that most of the increases in network capacity would need to come from building out more and more fiber, more and more capacity. But at the same time that all that capacity was building out, network speeds were increasing rapidly. Ethernet speeds actually increased by 100x from 1995 to 2002. So when you couple the 100x gain in technology with the volume build out in fiber, there was actually a 186,000 time increase in fiber capacity during this time frame. And so as we exited the early 2000s, only 2.7% of the fiber capacity was actually being utilized in the US. But by having all of that really, really cheap capacity, we saw the rise of new business models. Streaming video has transformed things. That wouldn't have been possible if there wasn't cheap fiber readily available. So even though these things sometimes are mismatched in time, they produce amazing productivity gains and amazing technology gains. So we will probably see a large overbuild. We will probably see technology advance faster than people expected, and the result will be a lot of long-term benefit. So now moving along to some of the even more recent tech build-outs, the birth of the cloud. So over the last 20 years, cloud has become the predominant way compute is deployed and provided out to workloads. It is the dominant compute usage model. And the cloud consists of massive amounts of distributed computing hardware, running software that's been decomposed, say, into microservices. It's decomposed into smaller chunks that makes it very, very scalable. So the result is services that can be seamlessly deployed on demand in a very elastic manner across the world. So developers can build applications incredibly rapidly. They can easily scale the individual components of those applications, all to meet changing user demand. So as an example, let's do something like ride hailing that we're all very familiar with. You probably have a ride hailing app on your phone. What happens there? There's thousands of individual microservices that are running. Those microservices are running across many, many servers in the cloud and to the edge, and they provide services that do everything from matching the rider to the driver, the payment services, billing when the ride is completed, all the things that are required. And all those individual elements can scale independently. So that helps to ensure that you always have capacity where you need it, when you need it. And so when building this overall service, you can size everything to the demand at the moment. It also means that you can scale your application and update your application seamlessly at any given time. The other beauty of this is that it means that you can run these applications within virtually any existing data center, and you can do so in an incredibly efficient manner as well. But one of the big challenges from a technology perspective during this time frame has been how do you scale general purpose compute to meet demands when some of the tricks that we've been able to play over the last couple of decades are no longer as effective as they once were. Processor frequency scaling has pretty much flattened out over the last 15 or 20 years. Having wider and wider cores, using more aggressive branch prediction to create more instruction level parallelism. A lot of these are no longer as effective and efficient as they once were. The end of Dennard scaling, that means that we no longer can play some of the same games from a power perspective. We are now paying the power cost from increasing IPC, say, within a given amount of silicon real estate. So that negates some of the performance gains that we have been seeing. So many of those techniques are no longer very effective, but the good news is there are a couple of techniques that we've been using over the last 10 or 15 years that have proven to be very, very effective. One of them is scaling out core count. So I talked about how the cloud runs. The cloud runs in a really elastic manner. You're building capacity or deploying capacity on demand to run various microservices. So scaling out cores is a very effective way to deliver that increased capacity. About 20 years ago was when the first multi-core CPUs made their way into the market. We now have CPUs that have as many as 192 cores. And when you look at things like accelerators, GPUs, you're really talking about thousands and thousands of cores that are running. So why does this work? As those microservices scale out, you add more compute resources. Those compute resources in the cloud are typically more VMs and more containers. So running more VMs, more containers means bringing more cores online. And this can be a very, very efficient way to deliver more and more performance. So rather than adding more processes to the same already overburdened cores, you just spread out across more and more cores, and that helps to relieve some of the data and compute bottlenecks that exist within the system. It can also be effective in helping to amortize a lot of the system level resources effectively if the right technologies are brought to bear from a fabric mesh perspective, and you can balance the system efficiently across a lot of cores. So the result is we do have some ways today to keep up with the growing demand for general purpose compute. But I made it 15 minutes in, I haven't talked about AI yet, so we'll switch gears to that and I'll show you how all of this ties back together again. So if we look back at the history of AI, I think as we all know, AI isn't new. AI has been around for 70 years, but the pace of the last 5 years has dwarfed the whole 70 years before it. We can go all the way back to 1950. Alan Turing wrote his seminal paper, Computing Machinery and Intelligence, and that was really the first time that some of these basic artificial intelligence questions were first asked. He posed the question, can machines think? And he proposed what he called the imitation game, basically a test for how you could determine whether computers could actually think. We now know this as the Turing test, basically a test to see whether you can fool a random person into thinking that a computer may in fact actually be a human. So if you cannot determine the difference between the two, you pass the Turing test, and what we now call artificial intelligence has been achieved. There were some advancements that occurred right after that point. So in 1951, Minsky and Edmonds, they built the first artificial neural network. This was called SNARC, the Stochastic Neural Analog Reinforcement Calculator. What it did was it modeled the learning processes that occur in the human brain, although be it much, much different than what we think of now as artificial intelligence. So in their test, what they were doing was they were replicating the way that a rat would run through a maze. So it had a reward, a punishment system, and a feedback loop, and using a machine that required 3,000 vacuum tubes, they were able to simulate 40 neuron-like units. So the first time that a crude neural network was built that could perform an actual task. In 1955, the term artificial intelligence was first used, which has now become the predominant way that we talk about this technology. And then in 1957, Rosenblatt built the perceptron. So the perceptron was an artificial neural network that enabled pattern recognition. And the key here is that it started to use multiple layers. So this used two different layers in its learning network, and it introduced for the first time a classifier that would learn from data by adjusting the weights within the algorithm. So even though it was very, very limited at the time, and it was really only capable of solving linearly separable problems, this did lay the foundation for a lot of the things that we now think of today around neural networks and machine learning. And then in 1969, Bryson and Ho, they introduced backpropagation. This is one of the critical algorithmic techniques that's used today. So they used this multi-stage system, and it was able to go back and calculate errors on the results after completing the training. And while this was only being used for control systems at the time, it ended up making its way into some future systems in 1986. So you can see there was about a 17-year period where artificial intelligence sort of hit this winter, where further advancements stalled, and there weren't a lot of useful applications for artificial intelligence. But then in 1986, some slow, steady progress began again. At that point, Rumelhard, Jeffrey Hinton, Williams, they published a paper called Learning Representation by Backpropagating Errors. This took that backpropagation technique a little bit further, and this time they actually applied backpropagation to a network, and it was able to be utilized for multi-layer neural networks, and was able to be applied to really complex patterns. So this really is the foundation for what we think of as modern deep learning. And this renewed interest in neural networks over the next couple of decades. In 1989, Jan LeCun, AT&T, Bell Labs, they successfully used the backpropagation technique within a neural network, and they did this to recognize handwritten zip codes. So for the first time, there was a useful application for some of these techniques. Handwritten zip codes could be recognized. You can imagine that this led to big productivity gains, and this demonstrated the potential of neural networks to be very effective in image problems. Then in 1997, IBM's Deep Blue, it beat the reigning world chess champion Garry Kasparov in 6 games. This was the first time that a computer had ever beaten a human under actual tournament chess conditions with real time limits applied. So this proved that computers could beat humans, not just in rote tasks like recognizing handwriting, but also in strategic tasks, which is something that we think of humans as being exceptionally well suited for. And this ability to calculate millions of moves per second, plus a lot of advancements that were programmed in around advancements in game theory, suddenly took artificial intelligence to another level, and this started to increase the public popularity of artificial intelligence as well. Then back in 2006, Geoffrey Hinton, he published Learning Multiple Layers of Representation. This was really the sum of a lot of the breakthroughs over the last couple decades in deep learning. It outlined how you could use multi-layer neural networks, train them more effectively, and the idea here, this paper kind of summarized the complete shift into what we now call deep learning. So now the shift to deep learning as a artificial intelligence technique was complete. And then in 2007, Fei-Fei Li and then other researchers at Princeton, they launched ImageNet. There's a huge database of annotated images that fit into thousands and thousands of predetermined categories. This fueled many, many years of image classification growth by having an easy-to-use common data set that researchers could draw from. Then in 2011, IBM's Watson, this was a natural language question answering computer. This then beat two of the most successful Jeopardy players in a live match, beat Ken Jennings and Brad Rutter. And this won because Watson added new abilities to process and interpret language and answer even more complex questions than had ever been posed to AI before. So this now proved that AI actually has the ability to interpret and to interact with human language on a fairly human level. In 2012, Geoffrey Hinton and some of the other researchers at the University of Toronto, they designed a convolutional neural network, or CNN. That had a huge breakthrough in image classification accuracy. The previous best results within ImageNet were 25% error rate. This brought that down to 16%. So this was a big turning point in computer vision. CNNs became incredibly popular in image recognition over the subsequent decade. And then in 2016, Google's AlphaGo beat Lee Sedol, which was one of the world's top Go players. If you're not familiar with Go, it's one of the most complex games in the world. The number of potential moves outnumbers the number of atoms in the universe. This was long seen as a game that would be impossible for a computer to beat a human at because of the complexity involved and the number of steps of problem solving and creativity that went into this game. So this proved that artificial intelligence could solve incredibly creative and complex problems even better than humans could. And this was really around this time, this is where we started to enter the large-scale model era. So I'll talk a little bit about one of the seminal moments in this time frame. In 2017, there were some big changes with how Google was bringing Google Translate to market. And as someone who travels a lot and is often in foreign countries, I was using Google Translate around this time, and suddenly Google Translate went from being kind of semi-useful and could sometimes get some of the words correct. All of a sudden, it was amazingly useful. It could start to pick up figures of speech. It could translate incredibly complex passages almost instantaneously. There were two things that were happening behind the scenes that allowed this to happen. One is previously they were using phrase-based machine translation, which was much more rules-based, which is why it wasn't really capable of handling incredibly complex or idiom-based speech. They moved to neural machine translation. When they did this, they saw large increases on the left there, large increases in translation capabilities across multiple languages. But the really big step was the following year in 2017 when Google introduced transformers. And this was the move from using RNNs and CNNs to a transformer-based model, which is really the basis of what we see today with large language models and the things that are happening around Gen AI. So RNNs were the typical network architecture for translation, and what they did is they processed things sequentially, either from left to right or right to left. And they read one single word at a time, And the problem with that is, while effective, it means that you need to go through multiple steps in order to translate an entire phrase. You keep step by step making new decisions in order to translate the entire sentence. And the more steps that are required, the harder it is to make all of those decisions. So as the phrases become longer and more complex, the processing time increases almost exponentially. So that RNN approach, that sequential nature, the problem is, one, it doesn't scale well. The other thing is that I mentioned that we were getting much more parallel, not only on general purpose compute, we were also starting to develop more and more parallel GPUs. Google had the TPU. The problem is that RNNs can't take advantage of those particularly well because it's incredibly serial and sequential, not parallel. Now, CNNs, convolutional neural networks, they are a little less sequential, but the problem there still is that as phrases get longer, CNNs still do require a proportionally longer amount of time for processing. So you still haven't broken this and found a much more efficient way of doing things. What happens, though, in contrast in a transformer, is that here you perform just a small constant number of steps. So it doesn't matter how long the phrase is, it's the same number of steps. So you scale really, really well. And what it does is it applies the self-attention mechanism, which directly models the relationships between all of the words against all of the other words all at the same time, regardless of where they're sitting in the phrase. So you no longer need to do this sequentially. You don't need to do everything left to right because it's the same number of steps. The amount of processing time doesn't necessarily need to increase. So what happens is, to figure out the representation, the translated representation of each word, it's being compared against every single other word all at the same time. The result of this is an attention score that basically shows how relevant each word is to each other word in the sentence. And this became the BERT model. So the BERT model is one of the first transformer models, and that's really the most popular way to perform natural language processing today. So by going to a different approach, we were able to take advantage of the parallel nature of the processing elements that were being built out at the time and come up with a more efficient way to translate phrases. Now, there were other developments that have happened over the last couple of years, some important ones. In 2000, OpenAI introduced GPT-3. This was a language model with 175 billion parameters. So this was, at the time, then the largest, most sophisticated AI model to date. And it does an amazing job of generating human-like text, engaging conversation, writing code, all the things that we've been playing with over the last couple of years sort of came out of that development in 2000. Now, the good thing is that even though models have increased in size, there have been other techniques that have been used that help to counter that trend. In 2023, Mistral released Mixtral 8x7b, and this uses what's called the mixture of experts approach. So in some ways, a more efficient approach that is not as computationally intense. And you can see up here, the performance of Mixtral was able to exceed that of Llama 270b on a range of popular benchmarks while using 5 times less active parameters. So a good example of a technique that actually helped to counteract some of the trend that we see here. So you can see there, over the last 70 years, we went through a period where computational requirements for AI was increasing at a somewhat steady pace. Then we then entered the deep learning era, and you see there an increase in the pace at which computational demands increased. And then in the last couple of years, we've entered the large-scale model phase, and now we see a step function increase in the computational requirements. So all of this has created new challenges, and so I'm going to explore a little bit what those new challenges were and how we can help to combat that. Now, there are some things from a model perspective and a training, an AI perspective, that have been done that help to combat this. So while there are models today that may be as large as 1 trillion plus parameter models, the latest DeepSeek models, for instance, in Llama 4, they focus on that mixture of experts approach. So they're able to reduce the number of parameters. For instance, when DeepSeek R1 was released in January, it was a 671 billion parameter model, but it was trained with, as they've claimed, 10x less compute resources than were used by Llama 3.1 by Meta. And what did they do? They took advantage of a couple of approaches. One is they used smaller precision, so they used floating point 8 instead of using something like FP16 or FP32. By reducing the parameter size, you're able to reduce the computational requirements, both for training and for inference. They also used model distillation. This helped them to take advantage of using less memory bandwidth than what was required in training other models. And what this demonstrates is that you can create a model that's competitive with large models like GPT and Llama while only consuming a fraction of the price and a fraction of the computing resources. And we've seen now some of those other models, Llama, GPT, are now starting to use some of these same techniques. Another technique that's being used as well is compressing the outputted models. You can do things to compress the KV store, reduce the amount of memory capacity required, and also reduce the memory bandwidth that's required. Because when you look today, the key challenges that we face from a computing perspective when running these large models, one is compute density. Compute density is incredibly important. It's also a bit more nuanced than that. So while the compute is highly parallel, it's also relying on slightly different types of algorithms than what we typically are performing when we're performing general purpose compute, running a web server, running a database. It's much more vector heavy, it's much more matrix heavy. So less scalar, more vector, more matrix operations, which is why you see a lot of accelerators being built that really focus on more and more vector and more matrix operations. Also, memory requirements have increased a lot. This is both capacity and bandwidth. Capacity requirements have increased because these models are huge, and you need to have enough memory to store not just the model parameters and weights, but also the KV cache that's being used while you're computing results. And memory bandwidth requirements have increased as well, which is why you see technologies like HBM or people using GDDR or LPDDR memory in addition to DDR memories is to address the memory bandwidth requirements, because you need to feed all of this data in incredibly rapidly, especially when you're running inference. There's high I/O requirements. Models are being loaded, especially on the inference side. Models are being loaded, they're being switched, new users are coming online, and so this requires a lot of network performance. And all of this leads to power and thermal constraints, which today is the single biggest constraint that we have in terms of building out more and more capacity. Now, when we talk about AI, there are two somewhat different problems that we're trying to solve. One is the training problem. Now, training, you can think of, that's computers sitting in a classroom learning how to perform some sort of a task. And this could take weeks, it could take months. So latency is measured in hours, days, weeks. And this is a massive problem that's being solved across thousands and thousands of nodes until a final trained model is produced. On the other hand, inference is the act of using those models. So think of it as now taking a test. Running inference needs to be much, much faster. Now we're talking about latency requirements in the millisecond range. And you're running many, many different models concurrently, perhaps. And so the scale of the problem is a little bit different. The scale of the training problem is building out one gigantic cluster that can train one model. And the problem that you're solving on the scale side with inference is how you can run billions and billions of models simultaneously for millions and millions of users. And this plays into the different ways that these problems need to be solved. When we look out into the future, while training has gotten a lot of the hype and a lot of the attention over the last couple of years because you have to train a model first before it's useful, as we look forward, a lot of the build out will be on the inference side. Perhaps as much as 4 times more capacity will be built out for inference than training. But as I noted, that capacity will probably take on a different form. Rather than large clusters that are highly networked together to run one single problem, we're now talking about thousands, millions of computers networked together, perhaps similarly to how the cloud is networked together to run inference. And these inference workloads will be running everywhere. They'll be running in big hyperscale data centers. They'll be running out at the edge. They're going to be running on the devices that are in your pockets as well. So this is a much, much different compute problem that we're trying to solve on the inference side. And it's a critical problem to solve given the fact that it will probably make up a larger percentage of overall power consumption over the long term than training will. There's also different ways that people are looking at running AI models today. Agentic AI is a new way of looking at how you might run an AI model. So instead of looking at it as one single model that's doing one specific task, you might have agents that are all running different types of tasks. So you might be asking it things like, book a trip to New York, book lunch for me, order me a new laptop. And you can imagine that the knowledge domains that each of these agents need is probably very, very different. The agent that is booking your trip to New York probably doesn't need to know anything about Russian literature. And so there's ways to economize these models and more efficiently deploy compute in taking advantage of some of these trends in the way AI is being deployed. And why does this matter? This matters because power consumption has increased rapidly over the last couple of years. To put it in perspective, between 2010 and 2018, even though we saw a 550% increase in compute demand around the world, there was only a 6% in global data center energy usage. So we did a really good job of efficiently building out more and more capacity without straining the grid, without consuming any more power. Now the issue is that the pace of growth and demand is faster today. The problems are more complex, and we've done a lot of the easy things to solve some of these problems. Data centers are incredibly efficient today. We've built bigger and bigger data centers. That helps you to amortize more and more of the cost and power consumption of data centers. So there's not a lot of easy things to be done anymore. Now the issue is that then between 2017 and 2021, if you look at the energy consumption of companies like Google, Meta, Microsoft, it grew 2 to 3x during that time frame, and AI was the biggest factor in that growth. The IEA, they are projecting that global electricity use from data centers will double between 2022 and 2026, so going up from 460 terawatt hours to over 1 terawatt hour. And they also project that the power consumption within the US will more than double by the end of the decade. So you can see there clearly a key problem for us to solve. Not only is this an environmental problem, it's a pure capacity problem. Now the other issues with this is that the increase in power demand on the grid is creating a lot of stress. In Ireland, for instance, data centers are already using 14% of Ireland's total power. And it's expected to increase by 30% between now and 2029. So there's countries where data center power consumption is actually taking power away from other industries. There's also potential concerns about the stress that this puts on the grid. As we get into the hot summer months when everyone's air conditioning is running, we'll probably see more and more examples where electric grids have a difficult time keeping up with the total power capacity. Weather disruptions will become more and more disruptive and impactful. And then we're seeing that more and more power is being brought online in ways that we probably weren't considering over the last couple of years. So there was just a deal announced recently from Microsoft that 3 Mile Island will be brought back up again. One of the units there will be brought back up and start producing nuclear power. So there's a lot of creative ways that people are going about solving these problems for the future. The other piece of this is from an environmental perspective, we have the pollution aspect of it. So a lot of the sources today of energy are not clean. They're relying on a lot of fossil fuel-based sources, especially when demand is high throughout the entire day. For instance, training a model the size of Llama 3.1, that produces the same amount of pollution as about 10,000 cars driving round trip between New York and LA. So this is not a trivial problem. Also, AI ends up impacting the water supply. There are over 160 AI data centers that have been built out over the past 3 years that are in places that are already dealing with scarce water or droughts. So this will only become worse as more and more water is used for cooling these data centers, especially within water-stressed regions. So, if we look at what we need to do to now address these problems, this is where we can start to draw some parallels from some of the previous phases. We see some of these previous patterns repeat themselves. We see insanely high forecasts with unimaginable demand. There's a frenzy of investment, growth at all costs. There's a lot of side effects, unintended consequences of this continued build out. Now, to be sure, AI is going to have a transformational benefit. It'll change the way the industries run. It'll change our productivity. But we have an opportunity right now to minimize some of the negative impacts. We can deploy these AI models in more and more places that will allow us to take advantage of greener power that's available in very dispersed regions and not typically all available in one location. We can apply things that like data pruning during AI model training, some of the techniques that I mentioned before, taking out unnecessary data that doesn't actually impact the accuracy of the model, but does require more and more power and more computing. We can use more parameter efficient models. So things like using the smaller llama models versus using the larger llama models. From a computer architecture perspective, there's an idea that we could make sustainability a computer system design principle. Today, we are fairly good at understanding what the environmental impact is of the individual data centers. The issue, there's a gap between the data center operator and the application developer or the person who's deploying the application. Applications aren't aware of what their performance limitations are exactly. It's unclear when you could make trade-offs in performance or make trade-offs in latency that don't impact overall performance that might greatly save power. So creating more power-aware capabilities both within servers, within data centers, and mapping that back to application software. There's a couple of projects out there today that aim at doing this, that would allow you to, at times, dial back compute performance or use a different compute configuration when a more energy-hungry compute solution isn't required. For example, today, a lot of times VMs and containers are deployed with a fixed amount of resources regardless of the task. So spinning up more containers just means spinning up more of the same resources. By putting more intelligence into applications, more performance counters, it could be possible to ensure that containers and VMs can scale to the actual performance requirements of the application, which not only saves money, but would really save energy. As an example, those things aren't always linked. Hard drives are a lot cheaper, for instance, than SSDs. So you could pick the cheapest instance with hard drives, but it's not going to be the most power efficient solution. The SSD solution is going to be the solution there. So even minimizing cost isn't necessarily always a proxy for improving environmental efficiency. The other thing that we'll see here is as we look at what we need to build out for on the inference side. So we will need to scale out across many regions for low user latency. There will be a need for many types of compute. So there will be a need for many types of solutions, many types of computational solutions. So we have a big challenge here and a big opportunity on the inference side. And I wanted to tie this back to what do we need to do from a silicon engineering perspective. There's a couple of things that I think we can do as a community that can tackle some of these problems. When we take a lot of what I talked about before and the types of solutions we're building, we have a lot more complexity from a design perspective than we ever did before. The size of the system has increased dramatically. We have multiple die making up an SoC. We have multiple types of compute coming into that SoC. Some of the solutions that we're building are highly integrated at the system level. So there's a lot of different building blocks that are being used, many devices making up the overall solution. And today's emulation and simulation tools can't accurately account for all of those different elements. They can't accurately perform system level verification across chip, package, platform. And so developing more and more complex tools that will help us to be able to emulate and simulate these solutions that are getting more and more complex is key. The other is that the memory and compute elements they have a very high power and thermal density. I mentioned HBM. HBM has a lot of memory bandwidth, but it's also very power hungry. That also makes it difficult from a thermal perspective. So better techniques to distribute power and distribute the thermal dissipation across wide areas while managing all the other design constraints, and better ways to model this is critical. So better power modeling, better thermal modeling, with all these various elements contributing to the problem, having better pre-silicon tools that are able to model with real-life workloads. These real-life workloads have become more and more complex and more varied over time. So being able to better model those will help to inform the design, and it'll also it'll also lead to less post-silicon miscorrelation to the pre-silicon modeled results. The other thing is I mentioned that data transfer is very, very important. So high bandwidth data transfer results in really large on-die interconnects, but it also means larger wire delays. And so we're starting to hit a lot of constraints when it comes to the interconnect itself. So more and more innovative approaches for more timing and power-friendly on-die buses. Today, we need to run these at higher and higher frequencies. That might mean more and more repeaters. This adds a lot of power tax to the overall system to hit the performance that you're looking for. So if you can reduce some of the overall power tax, that'll open up the degrees of freedom in innovation. The other thing is that these massively parallel non-deterministic computing elements are really, really difficult to model. So there's a lot of dependencies. You have a lot of data paths. Changing certain bottlenecks may not produce a linear response. So there's nonlinear responses to system level changes that you're making. And this means it can be really difficult to find race conditions. It can be hard to find deadlocks and live locks. So better approaches that will help to model out these incredibly complex, super parallel systems that are much more non-deterministic than the systems that we've been modeling in the past. So there's a number of approaches that I think would be beneficial here as we're tackling some of the challenges that confront us today. So I'll wrap it up with, if we look at the past trends, we know that there are huge bursts of technological innovation. They tend to come in short periods of time. I think we're sitting in one of those periods of time right now around AI. So the pace of change that we'll see over the next couple of years will probably dwarf anything we've seen in our lifetime. There's an outsized financial investment. That's a great thing. Take advantage of the fact that there's a lot of money out there, a lot of investment in finding solutions and building out capacity. There are investments that can be made in making advancements in the tools that we use and the techniques that we use. The impacts of what we build today are going to be long lasting. The things that we do today when we're building out AI infrastructure could impact the way that things look 150 years from now, like the gold rush still impacts the way that our landscape looks today and the way that society has built up. So it's critical that we address those impacts today in a sustainable manner and build efficient solutions that are responsible. I know here with the brain power that we have in the room and with the amazing companies here, I'm confident that we'll be able to innovate and take advantage of this new golden era of AI and do so in a responsible and sustainable way. So thank you. Appreciate everybody's time and enjoy the rest of the conference.